Okay, the first lesson in this unit is on equidistance theorems. We're going to split this up into two parts. Our targets are I can state the equidistance theorems, and then secondly, I can apply those equidistance theorems in proofs and to solve other problems. All right, so we have to go over a little bit of vocabulary first. We have this idea of a perpendicular bisector that we're going to talk a lot about in this unit. So as you might expect, a line, let's say here, or technically it could also be a ray or a segment. So it could be either one of those. That is both perpendicular to the segment and, so both of these things, bisects the segment, is a perpendicular bisector. So we're kind of coupling two ideas together. So it has to be of a segment. So if I have that segment and I want this line to be the perpendicular bisector, this line would be the perpendicular bisector. We would have to know that it's perpendicular, so I'd have to have some right angles, and I would also have to know that it bisected it, so I'd have to know that those two segments were congruent. So that is a perpendicular bisector of the segment. We have this other idea that you see in the title of the lesson called equidistant. If you just look at the word equa, right, meaning equal, distances, right, that's exactly what equidistant means. So we are going to say if a point is equidistant from the endpoints of a segment, then the distances to each endpoint are equal. In other words, equal distances. So let me give you an example. Right? Let's say we have segment AB, and I'm going to say C is equidistant from AB. What that means, that is, if I pick some point C, the distance to A has to be equal to the distance to B. Equidistant. These distances to the endpoints of the segment are the same. That's what equidistant means. All right, so let's see if we can figure out what this theorem is that we're talking about. If you have a couple of different colored pens, it will help. So in line 1, I say connect point A to the endpoints of the segment using the red pencil. So I probably should be using a ruler, but I'm just going to draw them in nicely if I can. And I'm going to do that on each one of these pictures. And then in part B, it says connect point B to the endpoints of the segment. I'm going to do that in blue. Again, probably should be using a ruler. So let's do all of those segments here. That looks like they're already kind of connected. Okay. And then it asks us to draw AB. So maybe I'll pull out a straight edge here. And I'm going to connect AB. And I want you to look at what kind of a line that looks like in relationship to the segment. All right, so hopefully, if you are looking at the purple lines I drew by connecting A and B, I hope you can see visually that it looks to be, in all cases, perpendicular to the segment, and it should also appear that it bisects the segment. So what we've created is actually a perpendicular bisector. Think about how we did it. We had a point A that was equidistant because these red segments were the same. We had a point B that was equidistant because these blue segments were the same. Same thing here. Point A is equidistant from the endpoints of the segment, as is point B. Same thing here. Point A equidistant from these 2 points. Point B equidistant from those 2 points. If I connect the 2 points, I create the perpendicular bisector. So the relationship between the line AB and the black segment, it is the perpendicular bisector, all right? And then to get a perpendicular bisector, let's fill that in here, you must have, here's the key, 2 points that are equidistant, that's why we worked on that word, from the endpoints of the segment. So again, looking up at your pictures, for example here, this point right here is equidistant from this endpoint and from this endpoint, because these two red distances are equal. And point B is equidistant from the endpoints of the segment, because this distance is equal to this distance. If you have two of those points, together they form the perpendicular bisector. All right, so let's turn the page and let's actually write that up as our theorem. It is the one theorem, good news, the only theorem we're going to work with in this lesson. So let's say it like this. If 2 points are equidistant from the endpoints of a segment, then they form the perpendicular bisector of that segment. Okay, so we can draw it up here again. Let's pick my segment AB. All right, so if I have some point C, and I'll use my colors again. So if I know CA is congruent to CB, and then let's say I have another point, we'll call it right here, I'll call it D, and if I know DA is congruent to DB, then by my theorem I know that this line CD is the perpendicular bisector of segment AB. So when we write it, the piece that comes at the end, that's the segment that is getting bisected, right? The first part, you could call it a segment or a line if you want, that's the one that is doing the perpendicular bisecting to the segment. That's the one that contains these points that are equidistant from the endpoints of the segment. All right, so let's see how we can apply it. Let's do a couple of proofs. Angle 1 congruent to angle 2, angle 3 congruent to angle 4. That's given, right? Let's look here what I'm trying to get. I need AE to be the perpendicular bisector of BD. So we usually like to take the segment, the last piece that I know I'm perpendicularly bisecting, and I want to darken that. And I'm going to box in, these are the 2 points that I need to be equidistant from. So I need 2 points that have the distance to B and the distance to D the same. That's what I'm going to need to get to create a perpendicular bisector. Let's mark what we have. Angle 1 and angle 2. I'm going to stop right there for a second. If I cover up the bottom part of this picture, that should look familiar from the last chapter, right? If angles are congruent, then sides are congruent. So I think I can say that AB is congruent to AD by if angles congruent, then sides congruent. Then I'm going to mark 3 congruent to 4. And I think I have the same thing. If I cover up the top part of the picture, don't I have another kind of isosceles triangle there? Well, I can use if angles, then sides. So I think that should tell me that DC is congruent to BC by that same reason. So I have these 2 congruent and these 2 congruent using if angles, then sides. Well, now let's go back. Remember, this is the segment, right? And I need points that are equidistant from B and D. So I'm going to ask you to look at point A for a minute. Isn't point A equidistant from B and D? Remember, equidistant means the distances are the same. And I have this one marked with a single mark and this one marked with a single mark. So point A is indeed equidistant. And if you look at your diagram, I think you can see the same is true with C. There's my blue set of lines. All right, C is equidistant from D and B. Those distances are the same. So I can employ my theorem up here if 2 points are equidistant. Have that. I have A and I have C are equidistant from B and D. Then together those 2 points, AC, must form the perpendicular bisector of BD by my theorem above. If 2 points, let's abbreviate here, equidistant, then form perpendicular bisector. Now you might be thinking, well, Mrs. Sweetwood, you marked AC and up here it says AE. All right. If we're thinking about AC, isn't AC part of the same line as AE? So that is okay because AC and AE will be equivalent in terms of those 3 points there are collinear. So you could say AC here if you want to say AE. This is going to be the same thing. All right, example 2 is one of those where we actually have to draw our own picture. See if I can get it on the screen here. It says, prove the line joining the vertex of an isosceles triangle. So some of you read these and think, well, I don't even know where to start. So the first thing I pick out here that's important is I need an isosceles triangle. So under diagram, I'm going to draw an isosceles triangle. And if I'm starting with that, that's part of my given. So I'm going to say triangle ABC is isosceles. All right, my base is BC. I could add that if you wanted. All right, and it says the line joining the vertex to the midpoint of the base. Well, this is my base, so I better put a midpoint of the base on my diagram. I'm going to call that D. So I know D is the midpoint of BC, and I need the line joining the vertex to the midpoint, so I better connect that. Is. Anytime you see the verb, that's where you know you're moving into what you're trying to prove. We're trying to prove it's perpendicular to the base. So look at my diagram. What is it that I'm trying to prove is perpendicular to the base? The line joining the vertex and the midpoint. That would be AD, I want to prove is perpendicular to BC. Well, the only way we know how to prove perpendicular is actually to prove that we have a perpendicular bisector. Otherwise, we have not really talked in any way, shape, or form yet as to how you prove perpendicular. So let's think about how we can prove a perpendicular bisector, because if we prove a perpendicular bisector, all we really care is the perpendicular part. If the bisect part is there, that's just an added bonus, but proving a perpendicular bisect is enough to just prove perpendicular. And they're going to ask that a lot in your homework. So we have triangle ABC is isos, and we have D is a midpoint of BC. I'm going to start with the midpoint. I know BD is congruent to DC. If midpoint then divides into 2 congruent segs. All right, so if I'm trying to prove a perpendicular bisector, all right, let's look back up. Remember, we need 2 points that are equidistant from the endpoints of the segment. Well, if I want this to be the perpendicular bisector of this segment, here's the segment I need to be the perpendicular bisector of, so I need to be equidistant from B and C, and I would argue that this just got me 1 point. Look at, don't I have D that's equidistant from C and B using the midpoint idea? Now I need another point. Well, the only other point I see on my diagram is A. So how am I going to get A equidistant from B and C? All right, isn't this word isosceles going to tell me that? Can't I say AB is congruent to AC? Because if a triangle is isos, then it has 2 congruent sides. So that gets me those 2 congruent. Now that makes me look at point A and know that point A is equidistant because that distance is equal to that distance. Now I have A that's equidistant from the endpoints of the segment. I have D that's equidistant from the endpoints of the segment. So together, those 2 points, A and D, form the perpendicular bisector of BC by my new theorem. If 2 points are equidistant, then they form the perpendicular bisector. Now again, this isn't exactly what's written here, but we definitely covered it. I have proved a perpendicular bisector of BC. I really only needed the perpendicular part. But again, the only way we know how to prove perpendicular right now is to prove a perpendicular bisector. So anytime you see that in the prove, know you're shooting for this. All right, let's try one more example. Oh, actually, I guess we got 2 here. I lied. Sorry about that. F is the midpoint of BC. We have a lot of given here. DB congruent to EC. DB perpendicular to DF. EC perpendicular to EF. All right, so F is a midpoint. I think I'm going to start right there. That means BF is congruent to BC. Oops, not. What am I doing? If midpoint then divides into 2 congruent segs. All right, now look, I'm trying to prove perpendicular. I want AF to be perpendicular to BC. So I'm thinking if I can establish a perpendicular bisector for BC, I can prove this. So I'm really trying to prove that AF is the perpendicular bisector of BC, and that will cover it. I would argue that I already have 1 point. I have point F that's equidistant from C and B. That's 1. I need a second point. Well, let's see what else I have. DB congruent to EC. Perpendiculars get me right angles. So I have right angles here and right angles here. I'm immediately drawn to these triangles because I have these 2 sides congruent. So I think these are the right angles that I'm going to focus on. So I'm going to say angle BDF and angle CEF are right angles. Whoops, this should have been 2 and this should have been 3. And I would say if perpendicular, then they form right angles. And then for 4, I think I can get the triangles congruent. And I'm not going to say these angles are congruent because I'm going to be using HLR. I have right angles, a hypotenuse, and a leg. So that's triangle BDF congruent to triangle CEF. And then the question is, well, how are those triangles going to help me get a second point, right? I have this point F. Well, the only other point on this line is A. So how do I get A equidistant from B and C? Looks like kind of a problem because AB and AC are not corresponding parts of these triangles. But think back to the last chapter and think back, why is it that I'm choosing angle B congruent to angle C as my corresponding parts? Give that thought for a minute. If triangle's congruent, then corresponding parts are congruent. What will angle B and angle C get me? Focus on the big triangle. If angles are congruent, then sides are congruent. So that will get me AB congruent to AC. If angles, then sides. So I would have this side congruent to this side. I think that means I now have my second point. Now I have point A equidistant from B and C. So I have 2 points, which I'm off the screen here. I have 2 points, point A and point F. A is equidistant, F is equidistant. So together, AF makes the perpendicular bisector of this segment, which is BC. That's the new theorem. If 2 points equidistant, then they form the perpendicular bisector. All right, I want to do this one yet too. This is a good one. This one will be a little quicker. ABCDE is equilateral and equiangular. That gives you a lot of information. And F is a midpoint of AE. Let's write that down for a minute. And then let's take a look at what we're trying to prove. I need FC to be the perpendicular bisector of BD. So here's my segment. I need points that are equidistant from B and D. Well, the only points I see that are even drawn in here that are equidistant is this point C has segments to B and D. This point, which is not even labeled, I guess. And the only other point on this segment is F. So I kind of think I need to connect F to D and F to B. So I'm going to draw FD and FB because that's a possible point that I want that's equidistant. So those are auxiliary lines. Equilateral gets all of these congruent. So let's say that. BC congruent to CD, congruent to DE, congruent to AE, congruent to BA. If equilateral, then all sides congruent. Well, I immediately think I'm in great shape because that gives me point A, or point C rather, equidistant from B and D because those two are congruent. Doesn't help me with A because A to B is not the same as A to D, right? Nor does it help me with E, but I'm coming back to F. I think I'd like to somehow get FB congruent to FD and I'd be in good shape. Let's use equiangular. That would get all the angles congruent. Give you a hint. I think I only want these. So think about that for a minute. Why am I only picking angle A congruent to angle E? If it's equiangular, then all angles are congruent. If you don't see it yet, look at the last piece of given. F is a midpoint. So doesn't that get me those two segments congruent? Write down that. FA congruent to FE using the midpoint. If midpoint, then two congruent segs, and I hope you see it now. You should be focusing in on these triangles. Right? I believe they are congruent by side angle side, so BAF congruent to triangle DEF by side angle side, and then using corresponding parts, I can get FB congruent to FD. If triangles congruent, then corresponding parts are congruent. You see why from the triangles? I'm picking this hint and this. By picking those two, aren't I establishing that F is equidistant from D and B? So now I have 2 points that are equidistant, C and F. So now I can say together F and C form the perpendicular bisector of that segment I was talking about, which is BD. So if 2 points equidistant, then they form the perpendicular bisector. All right, that's it for this first part.